Hi, we're Team 39. In this brief video presentation, we will provide an overview of the techniques that we've used to create a player for the Yinsh game. We will also provide future directions on how to improve our player and a live demo of our currently best performing player. The first technique that we've implemented is heuristic search. The reason is that we wanted a more sophisticated baseline to train our subsequent algorithms on, and that was relatively quick and straightforward to implement. However, we've faced significant challenges, mostly that the state space for this game is significantly large, thus we had to make important trade-offs in how many states we could expand. The heuristic function is at the heart of our algorithm, and it's relatively sophisticated. It has hard-coded rules that come from our intuition in developing a sound strategy to win the Yinsh game. For example, our heuristic function positively rewards the player when he places rings close to each other, especially positioned in the center of the board, or markers that are placed consecutively. It also positively rewards actions or states that try to block an opponent from winning a ring. Finally, our heuristic also makes sure that if our agent has the chance to win a ring, it executes that action.
So another approach that we tried was Q-learning, and we expected this to be able to train Q tables for reasonable policies in an offline approach, which we could then use in a policy following agent or as initialization for other techniques that use Q tables. Now Yinsh has a huge state space and rewards are pretty sparse, so we used potential-based reward shaping based on the heuristics that we'd already derived. And we also tried a number of reductions to the state space. So one option was ignoring the opponent markers. We also swapped markers when playing as the alternate player so that you didn't have to train each player separately. It was an issue that Q tables grew large extremely quickly. So we had a number of optimizations, hashing the key, discarding entries that were zero, which led to significant savings, but was still getting us big files, so sort of 10 to 100 megabytes for 10,000 episodes. And after all of this exploration, we still found heuristic search to be much stronger.
The third agent we decided to implement is a Monte Carlo tree search. We expected it to be a strong player in Yinsh because it's the main algorithm used in AlphaGo, and the state space in Go is way larger than Yinsh. In the actual implementation for the simulation, I limited it to only run through the 3 more steps from the current state to prevent timeout. The Monte Carlo tree search doesn't have much success. It was not even able to beat the heuristic agent. The potential reasons for the bad performance are the limited time each turn, the random selection of opponent's move, and the Q table does not contain enough information. We have tried to improve the third point by implementing a heuristic function in the simulation, but the result is still not successful.
For some of the future work, a simple idea is to look at reducing the state space by considering that the board orientation doesn't matter. There are 6 rotations of the board that you can treat as identical. You can also simplify the simulation, which would help to speed up learning and allow deeper search in Monte Carlo tree search and Q-learning. You could also just consider the opponent's best moves when you're searching, which will lead to stronger heuristics. Another approach is to look at more training to help produce a better Q function initialization and give a stronger start point for the Monte Carlo tree search.
Okay, so let's run a quick demo of the heuristic search agent against the policy following agent with a Q table initialized from Q learning with a slight delay so that we can see the moves better. So you can see the heuristic agent puts its rings near the center and is very quickly collecting 2 rings while the Q learning based agent hasn't achieved any rings at all. So quite a strong result there.